very pedagogic introduction, okay, to constraint systems.
Sir, can all the written stuff be on those two boards?
Okay, because there will be only written stuff, so only the two boards. Okay. Except that line. That line has to be written here again.
No, sir, it's fine.
That is fine. Now you see, the point is this constraint system is one of the most important topics if you want to do any meaningful quantization of a theory. Okay, it is usually not taught, although it could be easily taught even in a BSc class, but it is not neither taught in BSc nor in MSc, hardly in post-MSc or anywhere else. You see, you have learned quantum field theory, and there are different methods of quantization, the so-called Lagrangian method, the so-called Hamiltonian method. Now, each method has its advantages and disadvantages. The Lagrangian method is a fully covariant approach to quantization. Okay, why? Because the Lagrangian itself is written in a covariant form. The Lagrangian is something like f mu nu f mu nu. Okay, so all variables, everything is written in a covariant form. What is the disadvantage of this? The disadvantage is that within the Lagrangian there are variables which are actually not variables. They are not genuine variables. They are something like Lagrange multipliers. They are not genuine variables in the sense that there is no time evolution associated with those variables. They are bad variables, and that is the reason you need to do some gauge fixing in order to avoid this. For instance, in Maxwell's theory, the A0 variable, A0, A1, A2, A3, the four variables of the vector potential, A0 is not really a very good variable. There is no time derivative appearing on A0. There is no equation of motion for A0. So that is a spurious type of variable. So this is a disadvantage. On the other hand, the Hamiltonian approach works with what are called only the dynamical degrees of freedom. It has all the correct dynamical degrees associated with it. The whole phase space is there. However, the disadvantage is that it is not covariant. Yes, why? Because the Hamiltonian is always discussed on what is called the equal time slice. So time is given a special preference. When you define the commutators or the Poisson brackets, they are what? They are basically at equal time. Now, it's a very complicated way you can define the brackets at unequal times, at all times. That's a relativistic definition of the Poisson bracket, which is not that familiar, or a relativistic definition of the commutator itself. But that is a very complicated way, and there are other ways of trying to discuss this problem. And that is the reason that more advanced stages of quantization were introduced. For instance, the Becky, Rowett, Stora and Tutin, the so-called BRST quantization. Then you have what is called the field anti-field quantization, the so-called Batalin, Tutin, Vygotsky methods. These are approaches which actually take the best of both the worlds. They can discuss it in a full theory, in a fully covariant approach, and also when only the correct dynamical degrees of freedom are there. That's the last stage. That's a very complicated, very complicated, developed by a whole group of physicists, Russia, Belgium, Argentina, and so on, also from India. Now, in order to appreciate all these issues and all these aspects, you should have some understanding of what is the constraint system, how do you go about discussing them, and so on and so forth. So that is what will be the essence or the motto of this lecture. Okay, now you first consider a very simple example. This is just a relativistic particle in two dimensions. Okay, so this is in two dimensions, that is it's a plane, say on a board, blackboard or the floor, and then you know the Lagrangian is just okay. Yes, it sets in the mass just equal to 1. is just a free, non-relativistic particle moving on the plane is defined by the following Lagrange. Okay, well, you know what are the equations of motion? You know how to do that. d dt of dl dx dot. And same for y. Same for y. So what will this give you? Okay, this is nothing but Newton's law. Force is equal to mass into acceleration, free particle. No force, this is 0, mass is 1, this is 1, this is the acceleration. Okay? X double dot is 0, y double dot is 0. Basically, Newton's laws have been reframed in the Lagrange equation. Okay, now there is no big deal. You can actually solve these equations. So these are just the arbitrary constant. The second order differential equation will be subjected to two constants. These are the integration constants, and they can be appropriately fixed by taking your boundary condition. So we say that if t is equal to 0, so the particle is at the location x0, y0, and then of course you can proceed. Actually, this will give you the time evolution. Okay. Now, for a free particle, therefore, that these equations of motion, coupled with a precise boundary condition, completely determines the motion of the system. Okay. So, if you know the value of x at any t, you can of course compute the value of x at any other t. Same thing for y and so on. Hello? Class হচ্ছে বলো right. So this is the standard Lagrangian formulation, which all of you know. You can pass to the Hamiltonian formulation. This was the Lagrangian version. Now let us do the Hamiltonian version of the same here. Model. So you have to define what is called the canonical momenta corresponding to the x coordinate, and this is given by this. So what is this? This is just x dot on the definition of L. Then how do you obtain the Hamiltonian? The canonical Hamiltonian is just hc is obtained by what is called the Legendre transform, and that is what? The momentum times the coordinate time derivative minus the Lagrange. Okay, so you should check for yourself that this will be this. So this is not difficult to see. You replace x dot by px, you replace y dot by py, and then you have px square plus py square, but you see there is this L has this x dot and y dot. You have to replace x dot again by px and y dot by py. The Hamiltonian is a function of only what? The momenta and what? The coordinates. Here of course the coordinates just doesn't come. It's a function of the coordinates x and p. The Lagrangian is a function of the coordinates and the velocity. Here again there is no, if there were a potential or something like that, you would have an explicit x, only the velocity is stuff here. Right. Now you can see that once given the Hamiltonian, you can now actually compute the time evolution of the phase space variables. These are called the phase space variables. The phase space variables are always double the configuration space variables. I mean, configuration space variables, you just say basically if you take just the coordinates x, so you say the phase space variables will be x and x. Okay. So you can compute the equation of motion x dot by doing what? By taking the Poisson bracket of this with the Hamiltonian, right? And what is this? Well, what is HC? HC is just this. And now you use the basic algebra. What is the basic algebra? X with x is 0, px with px is 0, x with px is what? Just 1. Okay? We are doing everything classically. There is no quantum as such. I'm doing with Poisson brackets. So, if x with px is just 1, you can simply read this off that this will be what? This will be x. Okay? Because it's x, the bracket with px, and the px is outside. Okay, so there will be two terms. So this will cancel the factor of half, and then x with px is 1. What remains outside is px. Similarly, x with py is of course 0. If you do y dot, you will get what? Py. If you do like this, y dot, you get y. Good. However, the story is not complete because you have to complete the whole sequence. We have computed the time evolution of the coordinates, but now you have to compute the time evolution of the momentum. So how do you do that? They said you have to do what? Px dot. And what is Px dot? That is Px with Hc. But Px with Hc is 0. Because Px with Px is 0, Px with Py is also 0. Now how to reproduce this set? This set can be reproduced. You replace Px by x dot. If you replace Px by x dot, then from here you get x double dot is equal to 0. Likewise, you can show that y double dot is equal to 0. Okay? So this shows that you can move freely from the Lagrangian description to the Hamiltonian description. You can also correctly reproduce your equations of motion either at the Lagrangian level or at the Hamiltonian. There is an important lesson here, and this is as follows. If you look at the first of the Hamilton's equations, you will see that this x dot is px, which is just this relation. See this relation. Therefore what? This is not an equation of motion. Although the textbook also says that these are Hamilton's equations of motion, the first set of the Hamilton's equations, the one which you do with the coordinates, is not an equation of motion. It's a definition of the momentum. Okay? What is an equation of motion? Suppose I just give you an arbitrary equation and ask you whether it is an equation of motion or not. How will you understand? Well, you must see that there must appear two time derivatives, otherwise it is not an equation of motion. Two time derivatives means there is an acceleration, there is a force term, or if not it is 0 or whatever it is, but the acceleration part has to be there. If there is no acceleration, well, of course it's not really an equation of motion, it's just a steady thing, there is nothing in it. Okay? So whenever there is an equation of motion, a double time derivative must appear. This just merely shows the remarkable genius of Isaac Newton when he, at one stroke, he wrote down that force, which is said as mass times acceleration, from which he got the equations of motion. But the acceleration actually involves the double time derivative, and therefore you see everything follows. In that sense, therefore, you must be careful in interpreting the Hamilton's equation. The first of Hamilton's equations of motion is a definition of the momentum. The second of the Hamilton's equation is genuine equation of motion, because there you can see immediately the acceleration will fall out. This is an important point. Okay. Now you will see that if I take an example, this is what? This is a very simple example which all of you know and which all of you understand. So I gave this example. Now I'll take an equally simple example and I will try to discuss some points which might not be that familiar. Okay, so we will take this example. Take the following leg line. C of half x dot minus y whole square. Good. So, please, if you compute the equation of motion, that is, if you compute the variation with respect to x, I've written just in terms of the action S, which is L dt. This just means d dt dl dx dot minus dl dx equals 0. If you write it in terms of the action only, this just equals this. So, what is this? This equation gives me x double dot minus, please check, is equal to 0, and for y, you will get this. So you see already there is some subtlety involved. The system has actually 2 degrees of freedom, x and y, but the 2 equations of motion are actually not independent. The first equation of motion is just a consequence of the second equation of motion. If you just take a time derivative on this equation, you will reproduce this other equation. Okay, alright, I'm sorry, there is a dot here. Can you reproduce these equations or not? Please tell me. You can reproduce this equation? পারবে বাঙালি পারবে can you do this or not? You cannot do this, then it's difficult for me to proceed like this. So you see the point. Please now try to understand. Now we are slowly entering into the terrain of constraint dynamics. I will slowly enter into it. There are 2 variables, but the 2 equations of motion are not independent. This equation is a consequence of this equation. You just take the time derivative, you will get this. That's the first point. Then, what is this equation? Is this an equation of motion or not? Not an equation of motion. No acceleration here. Therefore, no dynamics. System has no dynamics. It's proved. It is proved. This system has no dynamics. What is it? Now, why it doesn't have dynamics? You have 2 equations of motion. This is just a consequence of this. So forget this. Okay? You look at this. This is the only equation. Unfortunately, this is not an equation of motion. There is no acceleration. We'll slowly try to understand the meaning. Therefore, there is really no general dynamics associated with this system. Now, the solutions for x and y, which will be subject to the constraint, which is this. So this is basically a constraint. Yeah? This is not an equation, it is a constraint. So you can see that this will be of this form. This chalk will actually bore us. You have to give me a better chalk. Actually, it's always breaking. Even if I write.
Sir, the chalk in the white box, which is good. Light pink.
Okay. So you see, the general equation. So if you take x dot minus y, this is 0. So x dot will give me what? Beta. This will cancel this term. Have a term like gamma t. This will cancel this term. Phi dot cancel this term. So this is the solution I can write for this, and this function phi t is actually arbitrary, except that it satisfies some certain conditions that we have actually given the boundary conditions are of course clear. These are the boundary conditions. Right? So you can see that, so x dot minus y has to be 0, so therefore if y0 is beta, x dot at 0 also has to be beta, and then you can see that if you put t equal to 0 here, you will get x0 is equal to alpha, subjected to this boundary condition of phi of 0 is equal to 0. So what I have written is this is the most general equation, solutions compatible with the set which I have written here. Now what happens? Now what happens is this, the presence of this, you see, the presence of actually phi t, it really implies that there is an arbitrariness in the solutions. You can fix this, say, alpha or beta or gamma or whatever that is by a choice of the boundary conditions, right? But you cannot fix this by just a simple choice of the boundary condition. This is what is called the gauge freedom. This, in more technical language, is called the gauge freedom of the solution. The solution is not unique. It is not unique, okay? Because of the presence of, this is a function of t. It is a function of t. It is not just some constant which you can fix by some boundary condition. Value at t0, 0, t to the 5. No. There is an arbitrariness in the solution. So this, you know, that there is an arbitrariness in the solution, and this is in contrast with this solution. Why? Because if you give me the boundary condition, then immediately I can fix all x and y on the non-relativistic plane. Okay, I could do that, but I could not do or cannot do it for this system. So there is a degree of freedom in the solutions. And you can clearly see that if I change, this is called a gauge transformation. If I change x by x minus phi and y by y minus d phi, okay? Where did that fellows go? It's sneaking out. Now you see, if you look at this change of variables, you see what happens. The Lagrangian remains the same. Is it true or not? If I do x dot, this is x dot minus phi dot, minus y plus phi dot, gone. So this is called a gauge transformation. This is called a gauge transformation, and that particular Lagrangian is invariant under this gauge transformation. And so, of course, if the Lagrangian is invariant under this gauge transformation, the equation of motion will also be invariant under this gauge transformation. So there is a freedom of the choice, the freedom of how you choose. There is no unique solution. Because what it means, if x is a solution, x minus phi will also be a solution. Phi is a function of t, remember, it's not a constant, which you can just scale up. Likewise, y has to go in this manner. Right. We will discuss about this gauge freedom more elaborately subsequently, but let me actually now come to the other point. What is the other point? The development of the Hamiltonian formulation. This was the Lagrangian formulation. Now we want to first call it. Okay. So as before, you define a momentum Px, which is del L by del x dot. What is that? X dot minus y. Okay, and Py del L now. So there are many points to note. What is the first one? The first point is this. The problem is that y dot cannot be inverted. When you develop the Hamiltonian formulation, x dot can be inverted. It is px plus y. Y dot cannot be. First point. Y dot cannot be inverted. This is the problem. This is the problem. Then this fellow is 0. Second, another problem. What is this? Another problem. Incompatible with the basic Poisson algebra. Why? Because ypy is what? What is ypy? U. Should be what? Ypy?
In this case it will be 0.
No. But in general, what is ypy? Y and py are canonically conjugate pairs. Then what is the bracket ypy? 1. Xpx is 1, ypy is 1. But here 0 equal to 1. Py is 0, so 0 equal to 1. Another problem. Another problem. Problem after problem. Oh, it is such a simple system. Such a simple system, and your brains are being completely rattled on what to do. You cannot invert y dot. It is incompatible with the basic Poisson algebra which you have known all your life. That ypy are supposed to be canonically conjugate pairs, but unfortunately ypy is 1, but py is 0. The left hand side is 0. Poisson bracket of anything is 0 is 0. Okay. Then let us see the last and the Moccum problem. How to define the Hamiltonian? Moccum, you know, Fernandez. Moccum means what? The real blow. The real blow actually. Now you see the blow. And the canonical Hamiltonian H is Px x dot plus Py y dot. Right. Now you see the fun. So x dot is no problem. So you just write Px and then Px plus y. This is Px plus y. Okay? Then Py y dot. Okay. You are saved because, okay, you may not invert y dot, but you say, okay, Py is 0. So this goes out. Okay, so this term goes out. Minus what? Minus L. So write that. Half x dot minus y is Px px.
X square.
Square. So what do we get? Px square by 2. Okay? Then let us compute x dot by bracketing with the Hamiltonian. So x with this term will give me what?
Px.
Will give me just px, and with this term will just give me y. But this is okay. This is, I will produce this equation at least. This is just this equation. What is y dot? What is y dot? Huh? Next one. What is y dot? 0. R ki chuna? 0. 0 R 0. 0. Finished. But you see, now you are in more trouble. Y dot is 0. Here y dot is x double dot. So it does not even agree with the Lagrange's equation. So everything is a total mess. You cannot even develop the Hamiltonian formulation. You cannot even develop the Hamiltonian formulation. You cannot define appropriately the canonical Hamiltonian, and so on and so forth. So here actually comes now the work of Dirac. So here actually this is yet another stroke of genius from Dirac, who actually does the following. He says that if the situation is like that you have constraints in the system, you can already guess from the Lagrange's equation, you can guess the constraint. That's from the Hamiltonian level also you can guess the constraint. This is actually a constraint because there is no velocity associated with this momentum. There is a particular velocity. If there is no velocity, you cannot ignore. That's basically just a constraint. A relation between the phase space variables is a constraint. I hope you know that. Yes? Particle moving on a circle, say, x square plus y square is equal to 1. It's a constraint. So on the phase space, any relation which involves the coordinates and the momenta is a constraint. It is not a constraint if you have a velocity entering into the game. This is not a constraint because there is a velocity. This is a constraint, right? This is a constraint. Now, so Dirac does this. He says if you have a constraint, there is no meaning of the canonical Hamiltonian. There is no meaning of the canonical Hamiltonian. First remark. This is a very important remark. This canonical Hamiltonian has no meaning. The reason is simple. You actually cannot invert the y dot. On the other hand, if you blindly say this, that I will just put this equal to 0, this is also not admissible because you see if you blindly do that, you do not reproduce the correct equations of motion and so on and so on. So what he does, he defines what is called, so we will proceed on this section of the board. He defines, this is the, now he has told you, he defines a thing which is called a total Hamiltonian. He defines a thing which is called total Hamiltonian. What is the total Hamiltonian? HT is HC plus the constraints of the system. So what is the constraint of the system? Hello? পরে এখন পরে ছটা so This is the constraint. So what he does, he introduces a Lagrange multiplier and he put in the constraint which is P1. Here there was only one constraint, so okay, only one thing has been put. If there were more constraints, you would have included all of them, each constraint being implemented by a corresponding Lagrange multiplier. These constraints, which directly follow from the Lagrangian, were termed by Dirac as primary constraints. Okay? So, this is a nomenclature. Huh?
What is primary constraint?
What is?
Primary constraint.
Primary constraint, you will slowly go to a chain of constraints. So first you should learn what is the meaning of a primary constraint. The primary constraint is the constraint which directly follows from the definition of the canonical momenta. When you will define the canonical momenta, not all of them are genuine momenta. A genuine momenta is one which identifies a momenta with a corresponding velocity. If it cannot do that, then it is a constraint. And it is called a primary constraint by Dirac's nomenclature. Here there is only one primary constraint, and this primary constraint will be implemented into the Hamiltonian as I have done there. So you realize why it does that. And this, and just as you see, I mean you should know this. This is this part at least you should know, that you have done even in classical mechanics or what is called the Lagrange multiplier and so on, that when you have constraints in the system, you know the variational principle, and you know also the variational principle with constraints, right? So variational principle, the least action you apply, and then you get the equation of motion. But on the other hand, if the variation principle is such that apart from the action you have stated that there is a constant, is moving, say, is moving a definite trajectory, then what do? You include the constraint, and you include the constraint by introducing certain Lagrange multiplier. But this lambda is nothing but a Lagrange multiplier. You can just think it in that term. Right? Then the next step comes. What is the next step? Well, the next step is that he introduces the notion of the weak and the strong equality. This is a very important notion. Weak strong okay. So he says that the bracket or the algebra of constraint or whatever you do is to be interpreted in a weak sense. So what does it mean? It means the following. Suppose I take this bracket. This is a Poisson bracket. I am not allowed to put this constraint equal to 0 inside the bracket. I am not allowed to put the constraint equal to 0 inside the bracket, right? So this is what is meant by a weak equality. The constraint Py will therefore be written like this. This is called a weak equality. A weak equality means that whenever this object is used in the calculation of a Poisson bracket, then you cannot substitute it or replace it by 0 inside the bracket. Fine. You can only use this when all brackets have been computed. So, if there is some algebra and you compute the algebra is done. That is, the bracket is out. There is no longer any bracket. Then on the right hand side you have something which says proportional to P1, 0. That you can set equal to 0. Okay? That is what is meant by weak equality. You cannot put that equality inside a Poisson bracket. Strong equality, as its name implies, can be substituted anywhere, either inside the Poisson bracket or outside the Poisson bracket. Okay, so this, with these two master strokes, actually Dirac solves the problem. Now you see there is no jhamela with the Poisson bracket. This is 1, so there is no problem, because this is only a weak equality. All constraints are weakly implemented. You cannot put therefore this equal to 0, right? Therefore this stands. It is indeed this. What is written on the board is true. It is this. However, if you compute, say, an object like xpy squared, what is that? Now this is xpy, or rather y, safer, times py, and then you have a factor of 2 terms. Ypy is 1, so this is 2py, but now the algebra is true. Here you can put equal to 0. Right? So this gives an important theorem, which is shown here in a very simple way, that the bracket associated with the square of a constant is always 0. The bracket associated with the square of a constraint is always 0. This is trivial. We proved, because if you have any constraint, say phi, which is like this, then bracket of anything with this is always 0. There is nothing to prove, because this is x of phi with phi, with a 2, and then you say whatever be the value of this, because this is outside, sitting outside, you can put now phi equal to 0 strongly on this here. Okay? So this is a calculational technique or an improvisation which was introduced by Dirac in order to solve this. So we are slowly entering into the regime, as I told you, of constraint systems. This is an example of constraint systems. So I hope you have understood one thing. You have understood the notion of total Hamiltonian. You have understood the notion of primary constraints, because first comes primary constraints, then you write the total Hamiltonian. And you have also understood the meaning of the strong and the weak equality. Okay. Now you can see we can actually now go and develop this example, but I will not do that. I will now, because I have discussed a specific example, I will now discuss from a very general point of view without any specific example. You have understood this. If there is an unconstrained system, a non-relativistic particle on the plane, there is no problem. In passing from the Lagrangian to the Hamiltonian, everything goes consistent. This is an example of a constrained system, and immediately you see the difficulties either in the Lagrangian approach or in the Hamiltonian approach. The passage from Lagrangian to Hamiltonian is highly ambiguous and controversial, and in order to avoid that, to give some meaning, Dirac defines what's called the total Hamiltonian, defines what is called the constraints and the weak and the strong equality. These are certain notions which you now know. Now we will discuss everything in general terms, right? So once we discuss the thing in general terms, then again we will come back to the example, so that you have a better feeling of what is going on and how, just by looking at the structure, you can realize whether it's a constraint system. In any case, all interesting problems of physics are constraint systems. Unconstrained systems are only the free system. Harmonic oscillator, the free particle, all these, just one or two examples. But anything else is a constraint system.
We cannot use strong equality for any constraint.
No, you cannot use the strong. Constraints are always implemented weakly. So this weak sign is there. All constraints are imposed weakly. We'll come to this discussion in more details when I discuss secondary constraints or tertiary. I've just introduced the notion here only of primary. We'll slowly see how you actually develop the whole chain of constraints, because if you are adept at handling constraints, then you can actually quickly do or at least appreciate many problems. So say all gauge field theory, Maxwell's theory, Young's theory, all these are constraint systems. Gravity, string theory, all these are constraint systems. So it is always nice to have some formulation where you can actually work with these systems. Okay, so I will actually very quickly discuss in general terms. So suppose you have a Lagrangian which is just a function of the generalized coordinates and the velocities. Okay. Then the Lagrange's equations of motion is this, right? And this L is function of this, so you can actually break that and you can actually write it just in this modified notations. So I can write this. I have taken this on that side, so I have just this part, and this is right? So, I hope you understand this. This Lagrangian is just a function of the coordinates and the velocities. Therefore, the total time derivative, I can write it as just QB dot this and QB double dot. That's all I have. So I've just rewritten this part, expanded it in this form. Okay. Now what? I can actually rewrite. This is just the equation of motion. I'm just working with the equation of motion in a slightly different way. Write this as this thing, and then okay, that's it. But this is basically just this stuff. Okay. So you can see now that this equation of motion, where is the acceleration? The acceleration actually contained here. This is the double dot. So you can uniquely determine all the accelerations and hence determine the complete dynamical evolution of the system, provided you can invert this object, right? If you can find an M inverse, I can multiply both sides by M inverse, and so therefore I will have this Q double dot expressed in terms of M inverse and like that. This is actually known as the Hessian. This is called the Hessian. And if this is not equal to 0, then what? Then you can invert M.A.B. So these are known as the non-singular systems. These are the non-singular systems, which I just gave an example. The free systems, the non-relativistic free particle and so on, where you can find all the dynamical evolutions. On the other hand, the much more interesting case is this. This is 0, and these are called the singular systems. Now it's trivial for you to see that if you had a Lagrangian like this, this was the Lagrangian for this non-relativistic case, then this Hessian M.A.B. you want to calculate the matrix. So what is this? This is how you write this. So this is just 1 and 2. Here is just x and y. So this is d2l dx dot. This is d2l dx dot dy dot. This is symmetric. This is the same. dy dot dx dot dy dot. This is the Hessian. And then what we will compute. So what is this? dl dx dot was x dot, and again, so that is 1. So this is 1, 0, 0, 1. And this is 1. Therefore, this is invertible. The determinant is not 0, and you can see that this is a non-singular system. You can just read off from the Hessian that it is indeed a non-singular system. It has a unique Cauchy problem, and so on and so forth. On the other hand, if you had this example, so now if you compute the Hessian, you will see that it's a bit different. So you have for x dot, right? So what is that? This is 1. This is what? 0. This is 0. Y dot is 0. The determinant is 1. Therefore, this is really a singular system. It's a constraint system. Okay? So this is a very simple way of hello, আচ্ছা আমি একটু পরে করছি। I hope you have understood this. Okay, this is a very simple way of determining the whether the system is singular. So let me stop here. Right? This is a good place to stop. Okay, so thank you very much.